So let's move on to maybe the more interesting solutions. Those are the traveling wave solutions, okay? So these are the ones for which, let's say, s is greater than 0, okay? Now what's interesting here, right? Again, we have v prime equals w, w prime equals minus sw minus v1 minus v. But remember that w has to equal 0 for v prime to equal 0. So that means that term goes away anyway. So we get the same equation for the w prime null climbs, okay? So for w prime equals 0, again, we get v1 minus v equals 0, or in other words, v is equal to 0 or 1, okay? And so we have vw is equal to 0, 0, 1, 0, okay? And we have a slightly different stability calculation in this case, okay? So now again, we're doing phase plane analysis, okay? Stability, okay, tells us to compute this Jacobian. So that's going to be 0, 1, minus 1 plus 2v. And now we have this minus s term here. So our eigenvalues are going to be given by lambda squared plus s plus 1 minus 2v is equal to 0. Okay. And so in the case of VW is equal to 1, 0, let's see what eigenvalues we get in that case. Well, we have, sorry, I missed a lambda here, excuse me. So in that case, we have lambda squared plus s lambda minus 1 is equal to 0. So that means that lambda plus or minus is equal to, right, just quadratic formula, squared plus 4, right? This thing's always bigger than s, so you're always going to have one positive and one negative eigenvalue, okay? So we have a saddle for VW equals 1, 0. What about 0, 0, okay? 0, 0 has the associated eigenvalue equation, lambda squared plus s lambda plus 1 equals 0, okay? So that is going to be lambda plus minus is equal to a half minus s plus minus now s squared minus 4. That's it, okay? Now, this is the cool thing that you get out of this phase plane analysis is that you learn something about the shape of the traveling wave based on the value of the speed that you guess for it, right? In the traveling wave ansatz, you just plug in the traveling wave coordinate. You don't specify the speed, right? So in the viscous-Burgers analysis that we did before, we sort of found ways to restrict what s should be. Here again, we get a restriction on what s can be by what's called a physicality constraint. We need positive solutions. So let me explain how that happens, right? This argument is going to be negative when s is less than 2, right? So when s is between 0 and 2, we have that this thing would be negative. So we're going to get an imaginary number coming out of that, but we have a negative real part. So we have a stable spiral, okay? And I'll sort of draw this in pictures shortly to explain why that would be a problem. Now, when s is greater than 2, this is going to be positive, okay? This is going to be negative, and then this thing is going to be less than s, because s squared minus 4, square root of that should be less than s, okay? So both of your eigenvalues should be negative, so you're going to have a stable node in that case, okay? So what this means is that if we go to these two different cases and we sketch them, W and V, okay? Now here I'm going to sketch here's our stable solution. Here's our unstable saddle, okay? Now let me do the case where S is between 0 and 2, okay? It turns out that the saddle, right, it has an unstable direction that goes this way. I'm not going through that analysis, but you can work out the eigenvalue, the eigenvectors associated with that eigenvalue. And it has an sorry, you can work out the eigenvectors associated with each eigenvalue. And it has a sorry, I'm confusing myself. I can't like talk and write at the same time. All right. So it has a stable direction that goes this way and an unstable direction that goes this way. What happens then is that this is going to shoot over here and it's going to spiral into this fixed point, okay? Now, this is always the transformation that you have to make in these models. You have to think about then, what does V look like as a function of psi? You're probably used to in ODEs thinking about the independent variable of these systems as being time. The independent variable of this system is not time, it's the wave coordinate, right? So as I go backwards on a trajectory, I'm going back in values of psi. So that would be back here. So what happens? Well, as I move forward in psi, right, the V value is falling, and I have a negative value for W, which is V prime. So that should be tracing out a front. But then look what happens. It dips below here, and it sort of oscillates until it gets back to V equals 0. So the problem with this, right, is that again, we attain some V less than 0 values. This is non-physical, okay? And so this means that we need to exclude speeds s less than 2, okay? Because we don't want to look for traveling wave solutions that have non-physical shape to them. There are other more technical ways essentially to show that this also causes problem in the original nonlinear PDE, but I won't go through that now. I think the non-physical explanation is more intuitive, okay? What about the other case? The other case, if S is greater than 2, I get in that case W and V. I have my two fixed points here, but this one now at 0, 0 is a stable node, and this one up here is a saddle, okay? And all it does is make a nice heteroclinic trajectory, okay? A cline, just a, like a contour or a line that goes from one fixed point to a different fixed point, okay? As opposed to the homoclinic trajectories that we saw in the case of solitons, right? So this is our heteroclinic trajectory, okay? And this has the shape of a physical traveling wave, right? So V psi now has a nice approach down, and you approach V equals 0, but never get below V equals 0 in this case, okay? So you have a physical traveling wave solution. V is strictly greater than 0. Okay, and in general, traveling wave solutions of Fisher's equation approach speed at this lower limit, s is equal to 2. So if you actually run numerical simulations of Fisher's equation, you will have, you start out with some random initial conditions, right? You need to have at least some, population in some area, right? So you could do something like this. If this is X and V here, and I start out with some population here, if I increase time, what I should see is that, sorry, I haven't drawn this so that it's intuitive. Everything will spread out, right? And you'll reach a traveling wave that has speed roughly s equals 2.
Would there be one traveling the other direction too?
Yeah, I've just drawn it off the edge of the screen. And the idea is that you're asymptotically approaching this solution that you've gotten from the phase plane analysis. So the phase plane analysis assumes that, yeah, as you go out to negative infinity, you just have the back of the front is there, right? And then as you go forward, eventually you're gonna decrease the value of population until you get out in front of the front where you have no population there. Okay. All right. So that's Fisher's equation. Questions about Fisher's equation? All right. So hopefully what you saw there is that you can learn a lot from phase plane analysis. You have to interpret the results with care. And you also have to remember that S here is a parameter that moves you from multiple different phase planes. And so for some problems, you have to pick the correct S so that you get a phase plane that makes sense in order to give you the shape of the wave that you need, which is either a heteroclinic or a homoclinic orbit. So the last equation that we'll look at, and I'll have to offload this to a recorded lecture, but I'll get us started on it, is the bistable equation. Okay, so let's just start